Hi, welcome back to another LeetCode problem. Today I want to walk you through the solution of LeetCode 50, which is about calculating x to the power n. And this is an interesting problem. I think this is quite a unique one. It combines understanding a little bit of math with a recursive call. And the key insight here is, how do we avoid multiplying the value x n times with itself? So let's jump into this, and the best way to start is to look at the constraints first. So what we have is we have a value x that we're going to raise to some power. It can be a negative or a positive value. It can also be 0. And we have the exponent itself, which can also be positive or negative, even though it will be an integer exponent. Now, there is a nice thing here, which is that if x is 0, then the exponent won't be negative, which is really good, because that means that we will never have the case where we have to divide 1 by 0. Cool. Now, the first insight that you should have when you look at this problem is that how do you deal with negative exponents? So we have two cases. First case is positive exponents or 0, and the other one is negative exponents. If we have a negative exponent, we should handle this as an edge case. And the way we deal with that is we just check if it's negative. So if n is smaller than 0, we're just going to return, well, we just call our own function, but we'll just pass in the positive version of the exponent, right? And now this looks good so far. But if you raise some value by a negative power, there, then that is equal to 1 divided by 4 raised to that power, but in the positive. So when we return, we need to return 1 divided by our function call with the positive exponent. Now the other edge case is, what do we do if x is 0? Well, 0 raised to any power is going to be 0. However, there is another edge case that if n is equal to 1, by convention, anything raised, if n is 0, anything raised to the 0th power is by convention 1. So we have to put that edge case in there as well. This is by convention. Okay, so now that we've dealt with all of the edge cases, let's deal with actually the computation. And how do we do this? Well, like I said, the first example could be, the first approach could be just multiply x n times with itself. That is not going to be very fast. But what we can do is we could say, well, if we compute x, x times x, we could reuse that result to compute x times x times x times x, etc., etc. And there is an algorithm called fast exponentiation that allows us to split this long product of x's into groups of product of x's. And each of these groups we can compute in a recursive call, so that we don't have to compute it over and over again. And we can reuse the results of these smaller computations to build the results of a larger computation. And the way that works is, if you imagine you have a value x raised to the, to the 5th power, you can write this as x times x to the 4th power. Or even better, because if you subtract 1 from 5, you know that you're going to get an even number for the exponent inside these brackets. So you would immediately know that you could break this down even further. Well, and how do you break down x to the 4th power? Simple. You just make it to x to the x squared times x squared. So what this gives you is a way to start to decompose the whole computation into a bracketed expression, and we're going to have one recursive call per bracket in our expression. So x times x squared is the same as x times x. And this is exactly what we will do in our little helper method, which I'm going to show you next. So we're going to have, Well, it's actually called fast exponentiation. That's what the algorithm is called. And it gets typically the value x and an exponent n. But because we have already our we have access to our x up here, we will just pass in n. And we will call this and with the parameter n. Now, we have to deal with that with the edge case, right? If we break down exponents until they become 1, or potentially even 0, that's basically our base case where we terminate the recursive call. So we can say if n equal 1, return x, or we could just say if n equals 0, return 1. Because if you break down what is x, well, x raised to the first power is the same as x raised to the 0th power times x. Because remember, x is now odd, so we have to pull out 1. One of these x's. X is odd, so we pull out one x, just like we did up here. And then we end up with an even exponent in here. So, and that is just a number, right? So this will be x times 1. X times 1. That's then the result. So, because that is the base case. And now we have the base case in here. Well, now we need to make a distinction, right? What is the exponent? Maybe I should write this as exponent, just to make it a little bit more clear. So if exponent is an even number, well, what do we return then? Like I said, we have to compute the result for, right, exponent. We divide our exponent by 2 and multiply and get the result for that and multiply that by that result. That's exactly what we do here. Now, if the exponent is not even, we have to return the same thing, except we have to multiply another x to the side of this. So this will be times x. And then that is everything we will need. Now you can see that we are calculating the same expression 4 times now here. So something that you could do is you could just add a cache here. That will that will allow the first recursive call to go through. And then the result will be stored for this function call with that exponent. So the second, third, and fourth time this is called, the result will be retrieved from the cache, and we're not going to go into the recursion. So this will need some space. And since we are dividing the exponent at every step by 2, we actually only have log of n steps. So the number of items in the cache and the number of recursive call is logarithmic with respect to the exponent. So if we run this now, so that passes. And let's submit this to see if it passes all of the tests. And it does, which is nice. So now, how can we simplify this? Because I think we can get rid of this cache. Although you could argue that because this is a recursive call, we're still going to use a stack space for every item. And since we only have log n recursive calls, we're already using log of n stack space. So we're not really optimizing anything here, but it's still nice to do this. So what we could do is we just pull out the computation here and like so, and then we just put that in here, TMP, and we do the same down here. So now we just make one recursive call, right? Which simplifies it. Now we can simplify this even more. We can have a result variable that we return. Return. And what we now do is we know that we have to multiply the result with itself. And we have to take care of the case when the exponent is odd. In this case, we just multiply x to the result. So now that is everything we need, really. I don't know if you like this type of indentation or not, but oops. Yeah, so if we run this again, you see that it passes. We submit this again. And that's how you do fast exponentiation, and you get a log n time and log n space complexity with respect to n being literally the exponent value. That's it.